Everyone. In this video, we're going to talk about some of the exceptions that we see for these trends in ionization energy. So we're looking at a figure from your book. You can see that as we go across a row of the periodic table, ionization energy increases, and as we go down the group, ionization energy decreases. That's true for the most part, but we do have some exceptions. If we look at the second row, ionization energy increases, but then it drops again. So I want to spend some time talking about this exception, beryllium and boron, and then you may notice another exception. As we move across the row, ionization energy increases, but then there's another exception right here for nitrogen and oxygen. And just as a reminder, remember that ionization energy is the energy needed to remove an electron from an element in the gas phase. So to write an equation for the ionization energy for beryllium, we would have beryllium in the gas phase, and we would be creating this beryllium ion and an electron. So how much energy is needed to remove an electron? That's what we mean by ionization energy. Again, as we go across the row, ionization energy increases. As we go down the group, ionization energy decreases, meaning that it's easier to remove an electron, and that's because these electrons down at the bottom of the periodic table are so far away from the nucleus. But let's get back to this exception. Why is the ionization energy of beryllium greater than that for boron? Well, maybe it would help if we wrote down the electron configuration. For beryllium, we're going to have a helium core, and it'll be 2s2, and for boron, it'll be a helium core, 2s2, 2p1. Now let me ask you this. For beryllium, what electron are we trying to remove? It's going to be one of these in the 2s subshell, isn't it? And for boron, what electron are we trying to remove? What does your intuition tell you? Is it one of these 2s's, or is it this 2p electron that's higher in energy? It's actually this electron that we're going to remove. And do you see why it's easier to remove this electron? Do you see why that is? It's easier to remove this electron because this electron is shielded by the 2s subshell. So that's why there's an exception here. When we go across the row, ionization energy increases, but the exception for beryllium and boron can be explained by looking at the electron configuration. This electron is easier to remove because it's shielded by the 2s subshell. The other exception we want to talk about is nitrogen and oxygen. So let's write the electron configuration for nitrogen. That'll be a helium core, 2s2, 2p, 3, and then for oxygen, it'll be that helium core, 2s2, 2p4. I still don't know if I can explain why the ionization energy for oxygen is less than that for nitrogen. In other words, it's easier to remove an electron from oxygen than it is from nitrogen. Maybe if I wrote the orbital diagram. So for nitrogen, we have a helium core, And then we have 2 electrons in the 2s subshell, and then 3 electrons in the 2p subshell. For oxygen, we have our helium core. We've got 2 electrons in the 2s subshell, and then 4 electrons in the 2p subshell. Does this help to explain why it's easier to remove an electron from oxygen compared to nitrogen? I think so. This is the electron that we're going to be removing, and it's easier to remove because you already have this crowded orbital. There's already so-called electron-electron repulsion in the orbital. You've got a crowded orbital here, so this electron is easier to remove from oxygen compared to one of these electrons in nitrogen. So I hope this video helped you to understand some of these exceptions. Again, there was nitrogen and oxygen, and then beryllium and boron. Hope that helped, and thanks for listening.